All right, our next section is 10.8, and it's called vectors. Whoops. All right, vectors. So what is a vector? A vector is different from a line segment in the fact that a vector shows magnitude and direction. First person who can post what that comes from gets a solid bonus point on your next quiz. All right, vectors show both magnitude and direction. So when we're talking about a vector, we want to specify, well, a line segment just shows, a line that has a beginning and an ending point. So that's what a line segment is. Well, a vector has a beginning and an ending point. But more specifically, we have an initial point, meaning that's a starting point, and we have a terminal point, meaning an ending point. And we have a direction. Because we know where we started and where we ended, we have a direction. That's why we say we have direction. Magnitude is the equivalent of length. So we know its length and we know the direction. And just a quick note, when we talk about magnitude, so let's just say we're going to label this. This is going to be P and Q. So P, Q, the way we label a vector first, the way we label a vector, thinking back to geometry, when it was a line segment, we put a little line over it. Well, when it's a vector, we put like a half arrow over it. Another way you might see it is in bold. It's hard for me to do that with the iPad here. But that would be another way to notate a vector. But I'll use the little half arrow there because it's clearer for me. So when we're talking about length, remember from the last section when we talked about length of, oh my goodness, what were we doing at 10.5? Polar. We're talking about complex numbers. I'm so sorry, I forgot. So we're talking about complex numbers, and when we talked about the length of those complex numbers, we used absolute value symbols. Well, we're going to do it very similarly with our vectors. We're going to say PQ and then the little vector. However, we're going to put a double absolute value line to notate the distance, the length of our vector or magnitude. All right, so we have to, if two vectors are going to be equivalent, they must have the same direction and magnitude. Equivalent, oops, I forgot my E. Equivalent vectors must have equal magnitude, and the same direction. All right, so let's look at an example that will give us, let me switch colors here. Let's say we've got, let me see if I can make it nice for you. 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. 1, 2, 3, 4. So we're going to start with one vector. We'll start right here, and it will go to 3, 2. 1, 2, 3, 1, 2. Right here. And we'll call this guy PQ. then we'll do a second vector. He's going to start at 1, 2, 1, 2 here. This is his initial point. And his terminal point is going to be 4, 4 is what I have. 4, 4. All right, so he goes that direction as well. And we're going to call him RS. RS. All right, so we have vector RS in red and vector PQ in blue. So if we want to find out whether or not these vectors are equivalent, we need to find, first of all, you can tell that the direction is the same, right? You can tell that they are both going same, whoops, that's blue, same direction. We can also find their magnitude, how long they are, by, it's essentially the distance formula. I know you all remember that from college algebra. The distance formula. When we talked about it in college algebra, this is how we wrote it. We said x2 minus x1 squared plus y2 minus y1 squared, and then the square root of that will give us the distance. Well, magnitude is similar. We're going to say, I'm going to label just for, no, we'll keep it. We'll keep it as is. We'll say the magnitude of RS will be, so we're going to say RS was, my 2 points were 3, no, sorry, 1, 2, 3, I think they were 4, 4. This one up here was 4, 4. I think that's what I wrote. And then 1, 2. Those were my 2 points. So let's find the magnitude of that guy. He would be 4 minus 1 squared plus 4 minus 2 squared, which will give me, so this guy here is 3 squared is 9. This is 2 squared is 4. So the square root of 13 is the magnitude of RS. Well, let's find the magnitude of PQ now. So PQ, let me write down those 2 points as well. I think I said they were 3, 2, 3, comma 2, and 0, 0 was the other one. He started at the origin. So the magnitude of PQ would be, changing the x's, 3 minus 0 squared plus the 2 minus 0 squared. And you can see this is still 3. 3 minus 0 is 3. 3 squared is 9. And then 2 minus 0 is 2. 2 squared is 4. Again, I don't know why I made my square root bar, my radical, so big. So square root of 13. So they have the very same magnitude, and they go in the same direction. Let's determine their slope just to confirm that they rise at the very same rate, though, because it could be that their slopes are very similar and not exactly the same. But let's just find out real quick. So the slope of the, I guess I have to roll this down a little bit, of the first pair of RS, I'm going to say the slope of RS vector would be change in y over change in x. So that would give me 2/3. All right, so let's find the slope of PQ. So the change in y, 2 minus 0, over the change in x, 3 minus 0. You can see that this is going to be the very same slope in both vectors. So they definitely have the same magnitude here, and the same direction based on those two slopes. All right. So